What connects the high-voltage hum of a city power grid to a pot of water boiling instantly on a flat, cool stove? They both rely on an invisible force that bridges the gap between motion and electricity. The relationship between those two forces was mapped out in 1831 by an English physicist named Michael Faraday. Faraday discovered that moving a magnet near a closed loop of wire, or changing its magnetic field in any way, induces an electromotive force, or EMF. That induced force is what drives a current to flow through the wire and light the bulb. By proving that simple physical motion can generate electricity across an invisible magnetic field, Faraday established the rule that powers nearly every electrical generator on Earth. The amount of voltage you generate depends entirely on the physical setup. According to Faraday's second law, if you increase the speed of the magnet's motion, or use a denser coil with more turns of wire, the magnitude of the induced voltage spikes. But this rule works both ways. If you run an alternating electrical current through that same single coil, the current itself generates a pulsating magnetic field that constantly expands and collapses around the wire. Because the magnetic field is changing, it induces a secondary voltage inside its own coil. This secondary EMF actually pushes back against the original current, a phenomenon known as self-inductance. This pushback is a basic property of physics. Electrical circuits naturally oppose any sudden change in the magnitude of the current flowing through them. If a single coil can induce a voltage against itself, what happens when we place a second entirely separate coil right next to it? The expanding magnetic field from the first coil reaches across empty space and sweeps through the turns of the second. This induces a voltage in that second circuit without the two wires ever physically touching, a process called mutual inductance. Engineers measure the efficiency of this connection using the coefficient of coupling, or K. In an open setup like this, a massive amount of the magnetic flux simply drifts off into the surrounding air, resulting in a loosely coupled system, where K is quite low. To fix this, you add an iron core. The metal acts like a highway for the magnetic field, preventing leakage and snapping the scattered flux into a tight, focused loop. The coils are now tightly coupled, and K approaches a perfect 1.0. Researchers and engineers have relied on the tight coupling of iron-wrapped coils to capture magnetic flux since the earliest laboratory tests of electromagnetism. Moving from an open air gap to a guided iron core is what allowed electrical design to scale up from simple desktop experiments to highly efficient large-scale energy transfer. Scaling up introduces a physical mapping problem. Because individual coils can be wound tightly clockwise or counterclockwise, looking at a dense circuit board makes it virtually impossible to predict exactly which direction the induced current will flow. To solve this, engineers rely on the dot convention. If you look at this schematic, you'll see two black dots placed at specific terminals of the coupled inductors. The rule is strict. If a current enters the dotted terminal of the first coil, the reference polarity of the mutual voltage is always positive at the dotted terminal of the second coil. With that one visual shorthand, designers can map out massive, complex alternating current grids and get the polarity right every time, without ever needing to inspect the physical wrapping of the wires. Once you control the polarity and the path of the field, you can design a true magnetic circuit, a completely closed loop built specifically to guide and manipulate magnetic flux. The ultimate application of these engineered paths sits inside the heavy industrial transformers that route alternating current through our power grids. Looking at a cross-section of a transformer core, you'll see a continuous iron loop, but engineers often design them with a small, intentional air gap. By combining multiple materials, like iron and air, they create a composite magnetic circuit. Just as electrical resistance dictates how easily current flows through a wire, magnetic reluctance dictates how strongly a specific material fights the flow of magnetic flux. To calculate the total reluctance of this composite circuit, engineers treat it exactly like adding resistors in a series electric circuit. They calculate the reluctance of the long iron path, calculate the reluctance of the tiny air gap, and simply add them together. By calculating the reluctance of massive composite materials and leveraging the mutual inductance of simple wire loops, engineers exert complete control over these invisible forces to power the modern world.
Let's study more, and like, share, and subscribe for such more content. And comment something you want to learn.